Okay, here we are with the U.S. Farms data, and we're going to do a regression. The first thing to do when you're doing a regression, unless you're told specifically what to look for, is to try to figure out what your dependent and what your independent variables are. What is your Y, that's your dependent, and what is your X or X's, your independent. And basically it boils down to this. What are the things that you are likely to know ahead of time, and what are the things that you won't? And here we have a chart that tells us per year what the average acreage per farm was. And assuming that there is a steady relationship, obviously, we generally are going to know what the year is. But what we won't know is what the average acreage per farm is. And that's what we're trying to figure out. So that's what we'll do. We'll say that the year is our independent variable and our average acreage per farm is our dependent variable. So I go to data, data analysis, pull down to regression, and click OK. So my Y is my dependent variable. So that's average acreage per farm. And my X is my independent variable. Now, because I included the headers, I'm going to click Labels. That tells it that the first row is the name by which this piece of data is to be known. And I'm going to leave everything else the way it is and click OK. Okay, we're looking at our regression output, and we have a lot of information here that is helpful for people who deal with statistics. But for our purposes, the main thing we're going to look at is the R squared. The R squared lets us know basically the percentage of the variation in the data that we regressed that is explained by this regression. And this is saying that 93% of our variation is explained by this regression, which is pretty good. The next thing I would ask you to look at is the p-value. Now, the p-value is basically the percentage chance that this factor is not related to the dependent variable. Now, with a p-value of 8.32867e negative 0.6, you may not know what that means. That's scientific notation. That's saying that basically this answer is equal to 8.32 times, well, to be honest, 8.32867 times 10 to the negative 6 power, which is a really small number. Okay, that's how scientific notation works. And you know that when you put something to the negative 10 power, you put 10 to a negative power, you start moving the decimal point over to the left. So basically this is 0.0 followed by 5 zeros. 0.50832.867. It's a really small number. It's way lower than 5%. 5% is usually the number I like to see for my p-values. I want them to be 5% or less. Both of the p-values for my intercept and my year are way less than that. So I can go ahead and create my equation. Now, my dependent variable, as I said, was average acreage. So average acreage is equal to, and what would my equation be? I basically go with these coefficients times the variable. So it will be equal to 4.7179 blah 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 times the year plus, now because this is the intercept, you don't say multiply times the intercept. In the form of y equals mx plus b, y is the average acreage, m is the 4.71, x is the year, and b is the coefficient of the intercept. And oh, wait a minute, 4.794. Okay. So this is plus a negative 8926. And if you add to a negative, it's the same thing as subtracting. So it's minus 8926 and some other stuff. So this is basically my equation for predicting how much acreage we would have per year. So according to this equation, the average acreage, we could create a box called year, we'd have another box called average acreage, and we would say it would be equal to 4.7179 blah 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 times the year plus the coefficient. So if the year is 2013, my average acreage in 2013 would be 571, 0.589,744. And this ends solving the U.S. Farms data problem.